Hi everyone, welcome to our video lecture on sections 10.1 and 10.2 dealing with sequences. In this video lecture, we'll be defining a sequence in two different ways, explicitly and recursively. We will also determine whether a sequence will converge or diverge. We will write down the formula for the nth term of a sequence, and lastly, we will define monotonic and bounded sequences. Now this is our first lesson in chapter 10, and it's going to be all about sequences and series. It's going to feel a little bit different from our previous chapters because there's not going to be a lot of focus on derivatives and integrals, although those will come into play when we move on to chapter 11. But for now, let's focus on what a sequence is. Alright, so a sequence is defined as a function whose domain is a set of positive integers. So like 1, 2, 3, 4, but it's an integer, so it's no fractions. Now as such, a sequence is a discrete function and not a continuous function. Not here very important. Now commonly sequences are represented by subscript notation rather than the function notation, as we'll see below. Now I wanted to give you here some examples of a continuous function. So an example of a continuous function could be an x squared, a quadratic function here. So we have f of x is equals to x squared, and you see here that x could be any real number. Now an example of a discrete function, aka a sequence, could be represented like this, f of n, but again we're going to be using subscript notation. So when we're talking about sequences, we're going to be using this notation. Now, the discrete function here is still in terms of n, so it's going to be here n squared. However, we're going to be using some new notation here. We're saying that n belongs to the set of all positive integers. So if you haven't seen this symbol, this z here is representing integers, and the plus here is representing that essentially you're only focusing on the positive integers. Okay, now, this example here with a sequence is an example of a sequence that is defined explicitly. That is, it is defined in terms of n. But we can also define a sequence recursively through a recursive formula, which is going to be a formula that defines each term of a sequence using the preceding terms. Now it's important that whenever you're using recursive formulas, you must always state the initial term or terms of a sequence. And here we have an example of a sequence that is defined recursively. So we have the initial term, a1 or a sub 1 is equals to 1, and now we have a sub n plus 1 is equals to 3 times a sub n plus 2. And this is important. We're defining a particular term in terms of the previous term. Now, to get familiarized with the notation that we're going to be using and the concept of sequences, let's take a look at a couple of examples here. Alright, so for our first example here, we want to go ahead and write down the first 5 terms of a given sequence, and we begin here with the sequence a sub n is equals to 3n minus 2. Alright, so to evaluate a sequence, all that we need to do here is simply plug in the values of n corresponding to the terms that we want. So if we want a 1, then that just means that we need to plug in 1 for n, so we're going to have here 3 times 1 minus 2. A sub 2 is going to be the same thing as 3 times 2 minus 2. The third term, plug in n equals to 3. We're going to have 3 times 3 minus 2. A sub 4, the fourth term, that means n is 4. And let's see, the last and final term, a sub 5, is going to be equals to 3 times 5 minus 2. Alright, now evaluating this ones, we should get the following values. Okay, so now that we got these values, how do we represent our solution? Well, we're dealing here with a sequence, so essentially we're getting a set of numbers, so our solution should be written in set notation. So open up here our key brace here, and our solution was, for the first term, we got 1, second term 4, third term 7, fourth term 10, and fifth term 13. And there we go. This one here is our solution. Now, I want you guys to get some practice and work on this next example. So I'm going to go ahead and let you pause the video in a second here, where you can go ahead and figure out, okay, what are going to be the first 5 terms of this next sequence? Now this next sequence, a sub n is equals to negative 1 raised to the n plus 1 times n all over n plus 1. It's looking a little bit more complicated than the first example that we tried, but it is the same type of process. We just go ahead and let our n be values from 1 to 5 and see what we get. Alright guys, so I'll let you pause the videos and let's see what we get. Welcome back. Alright, so these are the first 5 terms that I got for this sequence. A positive 1/2, a negative 2/3, positive 3/4, negative 4/5, and a positive 5/6. Now I want you to note that it looks like for this particular sequence, you were alternating signs as you went from one term to the next. Can you see why? Well, you probably guessed it. It had to do with the -1 being raised to a power. If -1 was raised to an even power, you get a positive, but if -1 was raised to an odd power, you got a negative. So that's a hint that I want to give you. If you notice that in a particular sequence, you're alternating signs, then it probably has to do with, or you should have, a -1 raised to a power in the formula for your sequence. Okay, so let's take a look at one more example, but this time around, let's take a look at an example of a sequence that is defined not explicitly, but recursively. Alrighty, so for this one here, we're being told that a1, the first term, is equals to 4, and then the a sub n plus 1 is equals to 2 times a sub n minus 3. Alright, the way I like to do these problems is by defining n. So I'm going to let n be equals to 1. Alright, so if my n is equals to 1, well, the a1 is not going to change, that's still 4, but now the a sub n plus 1 is really the same thing as a sub 1 plus 1, but that's really just a 2, and that's equals to 2 times a sub 1 minus 3, which is going to give us, let's see here, 2 times a sub 1, but we know that a sub 1 was 4, and in fact, I'll put this one here in a different color. Okay, and then we're subtracting 3, so that should give us 2 times 4 is 8 minus 3 is 5. Alright, so now we know what a2 is. Now put this one here in also a different color. Okay, now for the next term, if n is equals to 2, well, we still know that a1 is 4 and a2 is 5, so the a sub n plus 1 is going to be a sub 2 plus 1 is 3, and that's going to be equals to 2 times a sub 2 minus 3, which is going to give us 2 times a sub 2, which we know it's 5, minus 3, which should give us a 7. Which I'll put here in a different color. Alrighty, now for the next term, if n is equals to 3, then our a sub n plus 1 is now a sub 4, which is equals to 2 times a sub 3. Which I'll put the subscript here in blue. Alright, minus 3. But we know that a sub 3 was 7, so we're going to get here a 2 times 7 minus 3, which should give us an 11 here. And again, I'll put it in a different color. Let's go for a light blue. Okay, now we have the first term, the second term, the third term, and the fourth term. So now let's go ahead and figure out the last and final term. So I'll let n equals to 4. So that's going to give us our fifth term. A sub 5 is equals to 2 times a sub 4 minus 3, which is going to give us 2 times a sub 4 was 11. Take away 3, and that should give us, I believe, a 19. Okay, so that means that our first 5 terms are 5, 7, 11, and 19. Whoops. Oh, I forgot our first term. There we go. Our first term was 4. There we go. Alrighty. Now, before continuing with sequences, I want to talk about the concept of factorials since it's going to come into play later. Now, some of you may have encountered factorials in the past, but if you've never seen them before, well, we're going to go over their definition here. Now, I want you to note that a factorial is really nothing more than a special product of an integer times its preceding integers, and I'll tell you what I mean by that. So here's the definition. If n is greater than or equal to 0 and it's an integer, then the factorial symbol, n, and you see the factorial symbol, it's an exclamation mark, but it is read as n factorial, is defined as following. So 0 factorial is equals to 1, 1 factorial is equals to 1. Those are the definitions here. If you're interested as why 0 factorial is equals to 1, you can ask me in class. Now, here is what we're going to be looking for. N factorial. So n factorial is defined in the following way. So it's going to be n times n minus 1 times n minus 2 times n minus 3 all the way to 1 if n is greater than or equal to 2. And this is what I meant here by a factorial being a special product of an integer times its preceding integers. So for example, if I gave you 4 factorial, then that's the same thing as 4 times the integers before it, so 3, 2, 1. So the answer would be 4 times 3 being 12 times 2 is 24. So there we go. 4 factorial is 24. Now, the way that I want you to think about the factorial formula is the following. n factorial is equals to n times n minus 1 factorial. And as we work on a couple of different problems, you'll see why this formula it's more convenient to write. Okay, so let's take a look at a couple of examples here. So the first example is asking us to figure out, okay, well, what's going to be 9 factorial divided by 7 factorial? Okay, so in order to get more familiarized with factorials, I'm going to go ahead and expand this out. So 9 factorial is going to be the same thing as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 factorial, which is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, as we expand it, you might have noticed that, hey, well, there's a lot of things that will cancel out. The 7s cancel, the 6s cancels, the 5s, the 4s, the 3s, the 2s, and the 1s. So really, you're just left with a 9 times 8, which is 72. Now, this one here is our final answer, but I would recommend not expanding them out if you can. So what I mean by that here is, rather than writing all of the multiplications here, we could have done the following. You could have taken a look at the larger number and expand that one out. So I'm going to have here a 9 factorial. That's going to be a 9 times 8 times 7. And this is where I'm going to stop, because I do notice that I have a 7 factorial on the bottom. So what we can do here is say, okay, well, as we were expanding out the 9, yes, we could have written it as 9 times 8 times 7, but we could have also just simplified our work here by saying that you're multiplying 9 times 8 times 7 factorial, and that way you can just go ahead and cancel out the 7 factorials, which should still give you this 9 times 8, which is 72. And there we go. This one here is our final answer. Now, if there's some other problems where you do want to expand out the factorials, I want to show you how to do it with a calculator. So lucky for us, the calculator can actually help us figure out factorials very quickly. So this is how we're going to be doing it. You want to go ahead and click on the number that you're interested in finding the factorial of, so 9. Then we want to go to Math and go all the way to the probability menu, where we see here a bunch of different options. Now notice that option 4 is the factorial symbol. So I'm just going to click here on 4, and there we go, 9 factorial. Now if you're interested, 9 factorial, it's actually, well, it's a pretty big number. Not too big, but it's a big number. But that's not a factorial. Anyways, going back to our problem, we're going to have here a 9 factorial. So let's see here, 9 factorial divided by 7 factorial. So we click on a 7, go back to Math, Probability, option 4, and there you go. 9 factorial divided by 7 factorial is equal to 72, which is exactly what we got. Okay, now let's go ahead and take a look at another example here. Okay, so for our next example, we have 12 factorial divided by 3 factorial times 10 factorial. Okay, so for this one, I'm going to use the shortcut that I mentioned above, and I see that I have a 12 factorial on the top and a 10 factorial on the bottom, so hopefully I can simplify these ones rather easily. So I'm going to go ahead and write down the 12 factorial as 12 times 11 times 10 factorial being divided here by a 3 factorial times a 10 factorial. And we get to see the 10 factorials cancel out, and now we just have a 12 times 11 divided by a 3 factorial, but 3 factorial is the same thing as 3 times 2 times 1, but I know this one is 6, so I can see here that, okay, well, I have 12 divided by 6, which is just going to give us a 2. So really, what we're working with is 2 times 11, which gives us 22. And that's it. Okay, now, if you're interested, you can always verify in your calculator. But now let's take a look at the next examples. Now the next examples, they look a little bit different now because we're not dealing with numbers anymore, but we're just dealing with the concept of factorials, exemplified here with just an n factorial. Alrighty, so taking a look at example C, how can we approach it? Alright, well, the thing is, I'm going to keep on using the same approach that I did before. Now, which was that approach? Take a look at the larger number, and then break that down so you can simplify it with some denominator. Now, if I take a look at our example here, we have n plus 1 factorial, which is going to be larger than n factorial because, well, this one is n, but then you're adding 1, so it's bigger. Alright, so breaking down this one here, the n plus 1 factorial could be written as n plus 1 times the preceding integer, which would have been an n, times an n minus 1 times an n minus 2, and we would have continued the pattern here. But lucky for us, there is no need, because if you take a look at a denominator, our denominator here is an n factorial, so I'm only going to be stopping at the n in the numerator. So we're just going to have here an n plus 1 times an n factorial, and you get to see here that, oh yeah, the n factorials cancel out, so our final answer is just n plus 1. Okay, alrighty, now for the last one, we have 3n minus 1 factorial divided by 3n plus 1 factorial. Now, I want you to try this one here, and I want you to use the same approach that we've been using in the previous two examples. Out of the two terms, or out of the values in the numerator and the denominator, which one is larger? Now, once you identify the larger one, start getting the factorials there to see what cancel out. Now, I'm going to let you guys pause the video here, and then we can compare our answers. Good luck! Welcome back. Alright, so hopefully this is the same answer that you got. Now, in this particular example, it was the denominator that was the larger value, so you had to break down the denominator. So 3n plus 1 factorial was the same thing as 3n plus 1 times 3n times 3n minus 1 factorial, and there we go, that's the term that we wanted because that was the term in the numerator. Canceling them out, we're left with 1 over 3 times n plus 1 times 3n. Okay, so this is where we're going to be stopping for this video, because I want to continue on part 2, talking about how we can recognize patterns for a sequence. Alright, so I'll see you in part 2. Have a good one.